Hello and welcome to this video. We are following the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian, and in this video we will solve exercises 3 and 4 of chapter number 2. Okay. First we will write the question. This is exercise number 3, and in this exercise we have to check which of the following binary operation which is binary operation are commutative. First, we have to see the definition of commutativity, that if A star B is equal to B star A, or all A B belongs to A, we say that this binary operation is commutative. Okay, the first question is, part A is, we have to check that subtraction of integers. We have to check that this the binary operation is commutative or not. We, as I have already told you, that to check, to prove any mathematical fact, we have to prove the general, but to disprove, it is enough to give one counter example. We take two integers, 3 and 5, and we have to see that to show that this binary operation subtraction is commutative, we have to check that either 3 minus 5 and 5 minus 3 both are equal or not. And it is clear that this is 2 minus 2 and this is 2, so they are not equal. So the conclusion is subtraction of integers is not commutative. Now part B, we have to check that division of non-zero real numbers. Okay, we take two real number, for example 3 and 7. We have to check that either 3 divided by 7 is equal to 7 divided by 3. So we know that 3 divided by 7 is equal to 3 over 7, and 7 divided by 3 is equal to 7 over 3. So it is clear that they are not equal. So it is not commutative. Okay, we move toward next question. The C part, we have to check that function composition of polynomial with real coefficients. We also give a counter example by taking f is equal to 2x plus 2 and another polynomial g, for example, it is x square. First we have to check the composition f of g, which is equal to f of g, means wherever there is x in f, we have to put the g. So it is 2x square plus 2. And now the g of f, which is equal to g of f, it is equal to 2x square plus 2, sorry, it is not square, 2x plus 2 whole square, because Wherever there is x in G, we have to put the whole value of f. And it is clear this is x 4x square plus 8x plus 4, and it is not equal to 2x square plus 2. So f of G is not equal to G of f in general. So it is non not commutative. Next is part D, multiplication of 2 cross 2 matrices with real coefficients. We have to check. We take two matrices, for example, 2, 3, 2 and 1, and the other matrix is 0, 2, 0, 0. If we multiply this, what we get? 0, 4, 0, and 4. And on the other hand, if we switch the positions, we get 4, 2, 0, 0. Clearly, these matrices are not equal. So the matrix multiplication with real coefficient is not commutative. Okay. The E part is, again, we have to check that exponentiation of integers. So we know that the exponential of integers is a star b means a to the power b, and we have to check that a star b and b star a are equal or not. So a star b means a to the power b, and b star a means b to the power a, and it seems it is clear that they are not equal. But we take an example. If we take a is equal to 2 and b is equal to, for example, 6, what we say, a star b, which is equal to 2 star 6, is equal to 2 to the power 6, which is equal to 64. On the other hand, b star a is equal to 6 star 2, which is equal to 6 square, which is 36, and they are not equal. So it is clear that in this case a star b is not equal to b star a. So the exponentiation of integer is not commutative. Okay, we move toward question number 4. And the question 4 is, which of the following sets are closed under the given operation? Okay, the set closure mean whenever we will apply binary operation to any two elements of the set, we will get again the element of set. The first part A is the set 0, 4, 8, 12 under addition modulo 16. It is easy to create the Cayley table, and from the Cayley table it is easy to check either this set is closed or not. Okay, here the addition is modulo 16. If we take when we add 4 to 0, we will get 4, and when we add 4 to 4, we will get 8, 12, and when we add 4 to 12, we will get 16, and that is 0 under modulo 16. Similarly, we can fill this whole table, and we see that whenever we apply this binary operation addition modulo 16 between any of the two elements of this set, we will get again the set of we will get again the element of this set. So this set is closed. We can the conclusion is closed under addition modulo 16. Okay. Part B. If we take the same set and if we want to check under the addition modulo 15, then we will see that it is not closed, because if we add 4 plus 12, that will be 16, and that will be congruent to 1 modulo 15, but this 1 does not belongs to the set. So the conclusion is the set is not closed under addition modulo 15, although this set was closed under addition modulo 16. Okay, we move toward the part C of exercise 4. We have to check this 1, 4, 7 and 13 under multiplication modulo 15. Okay, it is easy to make the Cal table for this set. Here the binary operation is multiplication modulo 15. We can write it as. Okay. When we multiply 1 with 1, it will be the same. And similarly, this one with this one, with all these elements, this will give the same. But when we multiply 4 with 4, we will get 16, but under modulo 15, it will be 1. And similarly, when we multiply 4, this 4, with this 7, we will get 28, but that will be 13 modulo 15. And similarly, it will be 7. And we can fill the rest of the table in the same way. And if we see that whenever we multiply two elements of this set under modulo 15, we get the result from the same set. So we can say that this set is closed under multiplication modulo 15. Okay, we move toward part D. We have to check that this set, same set 1, 4, 5, 7, but with the different binary operation under multiplication modulo 9. And as I have already told you that to disprove any mathematical fact, we need to give only one counterexample. And if we take 4 into 5 and this multiplication is under modulo 9, we get 20, but that is congruent to 2 modulo 9. And this 2 does not belongs to this set. So we can say that this set is not closed. This set 1, 4, 5 and 7 is not closed under multiplication modulo 9. So that's all about today's video. If this video is helpful and interesting, please subscribe the channel and like the video. See you next time.